Oh, wow. Okay.
Thomas will give a talk from here, I guess, because he doesn't have a tablet.
Okay.
1, 2, 3.
Добрый день.
Добрый день.
Hello.
Hello. So now, is it only me? No, yeah. The
No. I'm just trying to understand what I have to do to, so that something appears on this whiteboard and I write. Okay.
So can anyone hear me?
Yes.
Yes, but there's something strange on the board. It's saying communicate with comments and press C. And I press C without any results. This is how it should be,
well,
or
at the same moment, I don't see any comments, and I see just the old Zoom whiteboard. I don't know.
Yeah.
no, they say more work, less clicks. Press Shift.
No, I see something else.
Okay, let me get out and get back. Oh no,
I don't know.
no, again.
So, Tomasz, can you write something, or it's a problem?
Yeah.
Yeah.
Okay, I see it.
Uh-huh.
Yeah, the handwriting is good, at least. I don't know how you achieved this.
Well, what do you mean?
I mean, that your handwriting is good. I don't know.
Well, I have this thing. And then in school they told us to write, you know, every letter many times.
That's how it goes.
Okay, so should I start?
I don't know. Maybe Vereshchagin is coming or not? Somebody knows.
No, normally he should, so he didn't say anything, so by default, I guess he should come, but maybe you can call him in Skype, maybe he forgot.
I can write him.
Here is
So
Vereshchagin, but
here is.
why cannot I write anything now? It was possible at some moment and now it's not. It's probably not a big deal, but if there is some reason.
Yeah, I have no idea.
So I see only the eraser thing.
You have to. I think there is a pen on the left of the screen,
No, just
like a small green pen.
Even I can write something.
okay, no small green pen at all. Okay, let me try again a third time.
Or well, okay. In any case, maybe let's start.
Okay, so I will start very slowly. Probably, I'm not sure if I even get today to what Sasha wrote in the abstract, but let's see. What will be talking about is this online learning framework. So let's introduce this game first. So we will have some game between two players, learner, or you can call him mathematician, and adversary or nature. And there is some, so what we will be considering is that for this game there is some set x. Sorry, that's weird. Some set x, which are our points. And we want these points to be labeled by 0 or 1. So we consider we have some class h. Oh, that's weird. Some class h, which is class of binary functions over x. And the idea is that the learner will, the adversary has some function in mind. Some function h from this set, big set big H. It's very weird. Sorry. So adversary has some function in his mind, and well, they will be playing over this function, and the goal of the learner is to guess what function, which age the adversary has chosen, and do it sufficiently quick. So what exactly is happening? We'll be playing in rounds, and each round goes according to the following scheme. So first, adversary gives some point x, and the learner is supposed to guess what is the label, the binary label on x. So learner, yeah, there is some very unexpected behavior here. So learner predicts value of h x, not knowing which h is the true one, but he makes some prediction using previous rounds, and after he makes this prediction, adversary reveals what h of x is, and learner receives penalty, which is exactly the difference of so let's call his prediction h. H hat x, and well, this is very hopeless. Okay, so sorry. The learner receives a penalty, which is just the difference between what he predicted and the true value of the function. And now the goal is what we
So
are
value
interested
of the functions are reals or what?
No, they're binary functions.
Ah, binary, okay.
Yeah, so this is either 0 or 1.
Yeah.
And so we can think that equivalently that these members of H are just subsets of X, and instead of a function H, the adversary just gives a point, and the learner is supposed to predict whether this point belongs to the set or not. And then the adversary reveals, yes, it belongs, or no, it doesn't belong. And well, if the learner is right, then he doesn't get any penalty. If he's wrong, he receives, he makes a mistake. And now the question is, if H is somehow limited, can learner have a strategy that will allow him to correctly guess the H, the function H, while making not many mistakes?
Maybe Sasha or Kolya could say we already had some talks for that settings, but of course I forget everything. And so, what do we already studied for this setting?
No, I
in
mean,
our
the first
previous
question is whether
talks.
the setting is clear. I don't know. So let's just try
Okay.
to understand this.
I think that at the end of the game, the learner should output just one function. And he wins if that function is the function which was chosen at the very beginning by the adversary, right?
Mm-hmm.
And the problem is how many questions you have to ask. But this is not the framework I knew. So I guess.
What is the difference between what you said? In your talk, we just counted the errors.
Not in my talk. I didn't deliver any talk about this. I meant the talk by Tomasz at CERN. And there were Oracle queries, I guess, and not this.
Well,
No. Okay, so here we just adversary chooses a function from the class, then it gives access. Each time learner gives a prediction of what is the value, and then we count the number of mistakes, and it's continuous infinitely long.
Can we see the previous slide, the setting? Because I already forgot the setting.
Yeah. It would be nice to see the slide indeed if it's possible.
Okay.
Yeah.
So adversary just reveals one value and not some function which is consistent with all queries.
No. But we are no, just a function. Yeah. And sorry, just a value. Yeah. So for now there is no consistency oracle, and we'll get there later. So
and we are interested not in the number of queries, but in the penalty, right?
Yeah, it's a function of number of queries, I guess.
What do we want to minimize? We want to minimize the penalty before
the number of mistakes.
Yes, is the correct function, right?
Yes. So we assume that the game goes for infinite time. The question is whether we can whether the learner can have a strategy which will guarantee him making only finitely many mistakes. So to get some intuition of what is happening, let's think about a very simple example where H consists of two functions. Well, what does it mean? That means that there is some point x where these functions differ. So there is some x, and there is one function that believes that the label there should be 1, and the other function that believes that it should be 0. So what can so is it possible in this scenario that for whatever function that the adversary chooses, the learner wins without making any mistake?
I guess not.
Exactly. It's not possible because Well, for instance, suppose that the strategy of the learner tells us, well, go to the left, so predict 1. Well, then there is a game in which the adversary selects the other function, and we already imposed, and he already made the learner to make one mistake. Well, suppose that we have now 4 functions.
For example, is it clear how to give a learner that makes at most one mistake? So
Yes, yeah, right.
I guess,
No,
I guess
while there is no difference in two functions, then we have no choice, and after that one difference, we know that which is correct. Yeah.
Yeah. So I guess
Yes.
we can generalize that observation to know that every finite, if h is finite, then just we have a strategy that makes at most that many mistakes as h has members. Because
Yeah,
we
but
can
for example,
try.
there is also a nice exercise. We just what if I have 3 functions? If I have 3 functions, I still can make just one mistake. But how to do that if I have 3 functions?
No, one should predict if there is a choice. One should predict the most popular value, which carries is valid for 2 functions but not for 1.
And why it works?
No, because
why
if either it's not an error, and then we get information for free, and only 2 candidates, or it is an error, and then we get only 1 candidate remaining, so we know.
Yeah.
Yeah, okay, so that's a very good intuition. So okay, so suppose that we have 4 functions, and in the example that Sasha said of 3 functions, we have, so there is one point x when at least 2 of these functions differ, and then we can expect that there is also some other points when another 2 functions differ. And if there are 4 functions, then we can hope that something like that happens, that we have actually 3 points, x1.
So what do we want to prove about for 4 functions? I'm lost.
Okay, so well, I want to give a my point is to give first a characterization of when it is possible that the learner makes a bounded number of mistakes. So okay, so now that we have this, I would like to see what has to let us try to understand what.
Yes, the point is that for
condition?
4 functions we might have 2 errors. We might
two
need
errors.
to do 2 errors. And we want to give an
So
example.
there is a strategy which guarantees at most 2 errors.
Well, first let's see that if we have.
That we are proving, or what? Just wait a bit.
Let's first see that we need at least 4 functions. We need at least 4 functions for the adversary to force 2 errors. So we already saw that.
So we say that if we have 3 functions, adversary, we can have a strategy which makes only 1 error. That's we are explaining now, or what?
No, we already know that if there are 3 functions, then there is a strategy which makes 1 error.
Yeah. Now we want
to see that if there are 4 functions, then I will show an example when the adversary can force 2 errors.
Why adversary can force 2 errors?
Yeah, but not for every class with 4 functions. There has to be a special condition satisfied. So we need to have.
But just it's very simple. Imagine we have for all 4 functions on 2 element set. And then, of course, we have 1x, and then we say something, adversary choose another value. We have another x, we say something, adversary has another value.
Yes,
This
that's
is what
a very good. Yeah, that's a very good example. But I would like us to have a. Okay, so let's try to generalize what's happening in this example. So we can think that we have some labeled tree.
Prove to something or give a definition, or what we are doing now?
We wanna, Sasha,
We wanna give a
we are now trying to formulate a general theorem, how many mistakes, what is the minimum number of mistakes for each, and then we are trying to define a notion that is needed for that.
Okay, so we start with the statement of the theorem or with the definition of the notion?
Well, we start with a definition.
Okay.
Yeah. Needed for the statement.
Okay, let's give the definition.
Okay, so I will say that H shatters a tree of depth D if there is a tree of a binary tree of depth D whose nodes are labeled with elements of X and each path in the tree is consistent with H.
Okay, let me start with simple questions. So, do you understand correctly that in this definition we have two parameters, H and D, and tree is not a parameter and it doesn't appear, we don't say that H shatters this tree, just H shatters a tree of depth D, it's a property of H and D.
Yes.
Yes, yes.
Exactly.
And
so
before
now,
we had in definition of Vapnik BC dimension, H shattered the set, which means that all numbers, all combinations were possible. And now H shatters a tree of depth there, D. Okay.
Yes, and so let's try to understand what I mean when I say that a path in the tree is consistent with H. So how this tree, this will be example. So we have some tree and some path, which is labeled with some points x1, x2, and so on. And this picture.
So this tree is a full binary tree of depth D, yeah?
Yes, it has to be full tree. Yeah.
Okay,
sorry.
let me say how let me say my guess. So
Okay.
what does it mean? That there is a vertex, there is a point x1 when our functions from H can take both values 0 and 1. And for each of these values, for 0 or for 1, if we fix this value, there is still some other point x2 when the remaining functions consistent with the first value are can take values 0 and 1. And for each of these fixed two values, we can find other vertex x3 where still there is freedom for the values, and up to length d. Yeah?
Yeah. But an important point is that, for example, for this, so we have x1 on top, but the point x2 in case 1, and in point, it can be another point for the case 0.
So the difference with Vapnik-Chervanenko's dimension is that maybe all the functions which have 0 at x1 they are diverge at some point x0, and if they take value 1, they diverge in other point x1.
Yeah. And what we can see is that well, this case of Vapnik-Chervanenko's is somehow a special case of this tree, because shattering a set, we can encode this set as a special kind of tree, where at each level we have only one point.
In each level, you mean every labels are all the same, like x1?
Yeah, so here we have 1 point, here we have another one, and so on. I mean, on this level, on each depth.
Okay. So is the definition clear? Anyone has questions or? Then I guess there is a theorem that H chat is a tree of depth D if and only if there is no strategy that guarantees at most D minus 1 error. Yeah?
Yes.
Yes.
H chatters a tree of depth D if and only if no strategy guarantees at most D minus 1 errors.
Yes, so let's write this theorem.
Let's write this theorem.
So
No strategy for learner. Okay, so now we have the theorem, and maybe someone can explain the proof of the theorem. For example, Kolya, can you explain the proof of the theorem?
In one direction.
Okay, let's start with this one direction.
Assume that there is a tree, consider any strategy of the learner, and then the adversary first asks about the value in the point x1. So we somehow respond, and then if we answer 0, then the adversary says that the value is actually 1 mistake. And then we restrict ourselves, I mean the adversary, with all the functions which go to the left, which are ones, and so on, until we until we make D errors, there is still a function which has the answers the adversary provided.
So it's important to note that the learner strategy for learner does not control the choice of access. The access is the choices of opponent. So if we have the tree,
Yeah.
we just start with this tree and follow this tree, keeping this existing functions as possibilities for this. Okay, but then I guess you can prove also in the other direction. I think. Let's try.
Not me.
No, I think you can, but if you don't
So in
want,
the
let's
other
try someone
direction,
else.
and the other direction, we need to prove that if there is a strategy, then there is no tree.
No, I think no. If there is a strategy, there is no tree. The same direction. We need to prove
If
that
there is no strategy, then there is a tree.
then there is a tree, but no strategy for learner means that there is a strategy for the opponent.
Right.
We don't even need probably the determinacy theorem. Martin,
Well,
determinacy.
maybe it
for
will be
this.
easier for us to think that, assume that there is a bound on D, on the D in H shatters a tree of depth D. So suppose that it doesn't shatter at any tree of depth D plus 1. And,
I don't know what this I completely understand. What is the bound for depth?
No, it's
depth
just
is fixed.
we can actually show that if there is no tree shatter
by
tree of depth D,
transposition.
Okay, but what
we
is
can
the
show-
problem? Just imagine there is no strategy for L that makes at most D minus 1 mistakes. Then there is a strategy for opponent which makes more mistakes. And the strategy starts with some x1.
And this x1 can't be used. Can't be used.
This will x1 will be the root of the tree.
No.
Why no?
Because I don't understand how to proceed. So okay, assume that
x1 is the root of the tree.
Okay.
And then the learner can choose, can say either 0 or 1. So to construct our tree further, we consider what are the answers of what says our strategy in the case of two choices of learner. Oh no! I understand. The learner is not obliged to make an error.
Right.
We count the total error, not the number of errors in a given moment. So something is more difficult.
So I think it's better even in this direction. So to show that if there is no shatter tree of depth D, then there is a strategy that makes it most D minus 1 mistake.
Right.
And
how you prove it?
Well, we could try to somehow adapt this idea before. In this example with free functions, what we did is somehow vote according to which functions are more, somehow according to a majority vote. But we can try to do this, but what we will become, we want to compare, so we have H and some X, and we can consider two subclasses H.
So we are doing what? We can consider what we assume
that
we
there is
construct.
no tree of depth D shattered, and we derive from that a strategy that makes it most D minus 1 mistake. So this strategy receives on X on input, and then we are saying that what the strategy
Yeah.
Okay, so in the example with free functions, what we did, we considered, we broke H in two parts: the parts that of the functions that label X with 1, and the other part which label with 0, and we looked, well, which class is larger. And well, in general, this doesn't work, but what we could do is we could compare what is the biggest depth of the tree shattered by each of these subclasses. So we look, we get some.
So, so you describe the strategy. Take x.
Yeah.
Then
Take x.
there are two possible values at x, and
Yeah,
so we
so
have two subclasses.
two
H's
subclasses.
which go through 0 at x, and h's which go through 1 to x.
Exactly.
And for each of these subclasses, we look whether they shatter a tree of depth d minus 1.
Well,
If they both do, then the original class shatters a tree of depth d by definition.
Yes.
If they don't do this, let's take the subclass which do not shatter the tree of depth d minus 1.
Not
and
exactly.
Predict another one.
So we will have that. So we'll take we know that it's not, so as you said, it's not possible that both of these classes shatter a tree of depth d minus 1. So we know that
so one of them is good, and so let's predict the value that corresponds to another one. So either we go to a good class and make one error, or we don't do anything but still have no errors and continue by induction.
Yeah, so what we want to do is
with this smaller class.
What we want to do is ask which class can shatter depths of bigger depth, and we choose the one that can shatter trees of larger depth. If they both can shatter trees of the same depth, then we just...
No, we don't care actually about any depth. What is important is depth d minus 1.
No, because it might be that on this x, both, it might be that they have both smaller, no?
Okay, then we can make any prediction, we don't care.
Yeah. Okay, so so we choose the one that has a bigger dimension, let's call it that way. And if we are right in our prediction, well, then nothing happens and we can continue as before. If we are wrong, that means that we made one mistake, but that also means that our true function is now in some class h prime, such that we know that it doesn't shatter a depth of 3 at least d minus 1. And indeed, we can continue by induction. That means in the next step, we again will be considering 2 subclasses of h prime on some new point x. We get some point x2 now. Again, we consider 2 subclasses, and we predict according to our strategy. And if we are wrong, we know that now the new subclass that we are in cannot shatter a tree of depth d minus 2. And since d is some finite number, eventually we run out of depth to run off, that we cannot shatter, and we end up with one function and start making mistakes.
Yeah. Okay, so let's make it. Let's check what is happening. So, for example, Georgi, are you here or not? Or who can explain this proof? No, then Kolya, you should explain it again. Did you understand the proof? Just switch
yes,
on the
yes,
mic.
yes.
Then repeat the proof, please.
We assume that now that there is no tree of depth, small depth, and we want to construct a strategy of learner. And the strategy is quite simple. So we receive some x from the adversary. We restrict all the function on x. There are two choices. Either the value is 0 or 1. We obtain two subclasses. And we take the subclass for which the dimension is smaller or higher. I guess higher. Higher. And we say the value which is shared by that class.
Yeah, but we actually don't need to do this. If the dimension are smaller, we just take the class which's dimension is at most d-1,
Okay.
and predict the other class.
Okay. So if we know in advance the dimension is at most d, then we know also that at least one of these two classes has dimension at most d-1, and we choose the value shared by another class. If we make an error, that means that we result in a good class with small dimension d-1, and we proceed.
And we used one error.
And yes, and we used one error.
And
otherwise, we learned in the class that has the same dimension, and in both cases we recurse.
But we have the value of x is already used, so we can continue. And if x is infinite, it's theoretically possible that we infinitely make many correct predictions,
right?
Never finish. But this is okay.
Yeah, and we just maintain the invariant. If we have made, say, k mistakes, then the dimension is at most d-k. At most d-k, and that because the dimension is non-negative, we can't make more than d errors in this way.
Yeah. So this is what you explained. Yeah.
Mm-hmm.
Okay. And this is more or less the theorem is somehow shows that the definition of shatters the tree of dimension is just the maximal number of errors. So it kind of a reformulation of the maximal number of errors just in terms of trees.
Yes.
So is it clear now? Okay, if let's then go further if everyone is happy with this.
Well, so I want to introduce eventually some specialization of this framework, but before that, so okay, we design some strategy, but depending on what age exactly is, this strategy might be a computable function, or might be might require some more computational power than a Turing machine.
Okay, so now we introduce some computable framework, and so we want to give a definition or formulate a theorem or do something, but just choose what you want to do.
I want to start by asking a question.
Oh, that's the best.
So, question. So suppose that that h is given as a recursively enumerable set of programs.
No, first of all, now X is infinite and it's a set of integers or constructive object, yeah?
Yes. Or let's say that these are just natural numbers.
Yeah.
And
H
we
is
have
a
some
set of programs, total programs or any programs.
total programs. We can assume that they are total. We have some enumeration. We know that a function is in H if and only if there is some program in this enumeration which computes exactly this function. And now my question is...
Just write that they are total, so we not forget, and this is clear, yeah.
Okay.
Yeah.
So my question is there a computable strategy for the learner that makes at most C mistakes for some C?
But what do we know about the dimension?
Dimension is
okay,
fine.
sorry,
So
right. Suppose, and of course, assume that the dimension of H is finite.
Well, of course, if it's not if it's infinite, there is no strategy that makes a finite number of mistakes.
Yeah, so we know that already from the previous theorem.
Okay, so Kolya, can you answer the question? There is a question.
I guess not. I mean, I guess there is a set of programs such that there is no computable strategy.
No.
I'm sure.
The theorem is that there is always exists such computable strategy. If the dimension is finite and H is given like that.
So I'm wrong. Sorry.
Yeah, so
no. Just it could be yes, could be no, but for some reason it's yes.
And this is kind of one of the results, main results of the talk, yeah.
Yeah, so I guess that's the question that motivated the results that I will be presenting later with some weird notions that I have to introduce, but this is the easy motivations behind it.
Okay, so somehow, but it is strange indeed, because imagine that just imagine we have kind of a game. The game, the opponent for the learner more or less determines the behavior of the programs. And then when the question is asked, and he waits until the learner gives some answer, and then in somewhere in the large, we define the program sequentially, and somewhere far away we can make them diverge
well, I don't understand. What are you trying to explain? You're trying to disprove? Did you give an example?
I try to explain why it seems that this should be false, and I ask you what is the error in this argument. Maybe not the argument, but in kind of.
I don't know. So it's hard to say because there is not really an argument. I mean, you have to then start giving some example and so on.
Okay, let me try to say. So first, this questions of this type seems to be more or less equivalent to a game, when one person, the learner, tries to implement the strategy, and the opponent tries to construct the set of the function to extend the set of the function more and more for bigger and bigger inputs. And it seems
Well,
that
I don't understand. So I guess if you want to, I understand, but then what I don't understand is that, well, I guess for the argument you have to start by saying, okay, so adversary have to start enumerate programs in H such that every computable strategy for L is fails. It makes a lot, I mean, more and more mistakes, and in the end, and I mean, for example, infinite number of mistakes, somehow like that. That I would
Yeah.
understand. And then, yes, then
So you say that the problem is that we cannot somehow diagonalize against all possible computable strategies. This is the problem.
So I mean, we can to some extent. So I guess maybe for to better understand what's going on, let's try to prove the following statement. There is a class.
But you already make a sentence that there is a strategy. Maybe want to prove this statement. If just to no.
Well, so I would like to give first. Maybe we could see how the diagonalization. How we could attempt a diagonalization.
No. But if the diagonalization fails, maybe we just prove the statement then.
Okay.
no, I mean,
well,
with
but
diagonalization, you can prove something that, for example, with dimension, you can construct a class with dimension n where you have to make 2 to the n mistakes. For example.
Yeah. But still there is a kind of finite bound.
Yeah.
Yeah.
And no, maybe we should prove this finite bound then.
Okay.
No,
I mean,
what is the right order? So just.
I mean, so there are two separate things that we could try to see. I guess since we have some limited amount of time, we could try to start proving that there is a bound, the upper bound, or we could try to understand why there is a class which has dimension d, but that every learner has to make at least 2 to the d mistakes.
Maybe we can start proving upper bound. I don't know, but can we just start proving it? What do you think? I mean, just in this setting.
Yeah, I guess.
So people prefer
And for
to
example,
start.
I don't know. It's already non-trivial when H has dimension 1, for example, right?
So we now
Or
are.
I mean,
So first of all, the decision is we now are proving that there exists a computable strategy that makes finitely many mistakes. Yeah.
yes,
Okay, so let's
so.
to warm up. Let's try to show that there is a strategy which works for the class if the dimension of the class is 1.
Okay, if dimension is the class is 0, it means that it just have only one function, and this function is computable, so there is no problem of making no mistakes.
Yeah. So the dimension H is
now
0.
Assume we have the dimension 1.
Yes.
What does
if we
it
have
mean?
dimension 1, in principle, there might be infinitely many functions. And if we just try to test them one by one in some stupid fashion, then this might not work to give us a bound.
No, but let's reason like this. Imagine the class, if class has only one function, then there is okay, it's okay. If the class has only two functions, then we first there are two computable functions, and then while we have take this to computable no.
Well, I don't know. Well, then, Sasha, no problem. We can predict according to the first one, and then when we are wrong, predict according to the second one.
And if we are no, but if we are wrong, maybe the second one.
Well, I mean, the second one is also computable function. We can
Yeah.
start. Well, you're considering the case when there are two functions in the class.
No, not exactly two, maybe more than two.
Ah, okay. Well, let's say that they're exactly two.
If they are exactly two, then it's also okay, because we predict according to one function, and when we fail, we know that we have another function, and so we can predict using this one.
Yeah. And one option, well, imagine that you now okay, now imagine that you have more than two.
But
For
just
example,
we
you
know
can
the
try
dimension
to
is
remember
one.
this algorithm from the last from the theorem. What was the algorithm from the theorem?
Yeah.
The algorithm from the theorem was to look where you receive x, and you look for the case where, well, in this case, one of them, like if there is a one subcase which still have dimension one, you have to predict according to it.
Yeah.
Right.
But of course, the problem is that we don't know what are the dimensions of the subclasses, and we cannot find this computably. Yeah.
Yeah.
But why not? So you can try to find a which of the two subcases has dimension one. How? Well, what's the
But
natural
maybe
idea?
if in fact both have dimension zero, we never will choose one of them.
Yeah, but what means that they both have dimension zero?
They are just only two functions. Yeah.
So you see that there are two cases. If there are just two functions, you can do it one way. If there are more than two functions, you can do that. So
Yeah.
so the question is, okay, so there was like an argument. Who understood this argument?
Argument
That
for
in
what?
that in case of dimension h is one, there is a computable strategy even with one mistake.
No, I think that I understand, but I'm not so sure.
But can you say that then?
But maybe somebody else understands. No. Okay. Let me try. Then just we consider non-constructively. We consider several cases. First case, if there is only one function in the class, then we can use this
Then it's
function.
computable, and we
Yeah,
can
if there are only two functions, we answer according to their common value, while they have a common value, and then choose one of them when they. If there are two values, we just take one value and either it is correct and then we know the function, or it's incorrect and then we again know the function, and the price is only one error. But the problem is if there is more than two functions.
Then there is a property that one of the restrictions always has dimension one. Because what happens if both restrictions have dimension zero?
Yeah, if we have at least three functions, this means that for every x, at least one of the values doesn't determine the function uniquely. And we can wait until this is found just by looking, enumerating all the programs for our set. And this can be done for every value of x. And when this happens, we choose this better value. No, but there is another.
Wait, I don't understand. What are you explaining? Once again, sorry.
So I think we choose the value which is compatible with at least two different functions.
Ah, yeah, that's true. And we can,
And
and how we can compute like this?
Maybe it's only one possible value, because all the functions all the functions go to this thing. But
okay, so once again, the algorithm is you obtain x and you choose the value which is consistent with two different functions from the class.
with at least two different functions.
And it exists
First, this should already exist, because if not, then there is no tree.
Yes. And then it exists.
If we don't make any
because
errors,
otherwise
then it's
there are just
okay.
two functions. So you have at least three functions, you have two subclasses, and at least one of them has two functions. That's right.
Yeah.
But the point is, okay, the other point is why it's impossible that both subclasses have two functions. So
no,
there is,
but it's possible. It will imply that the tree has dimension 2.
Yeah. So in our case, it's impossible. So okay. So when we have at least three functions, then always one of the classes has at least two functions, and the other has at most one.
No, so it's not guaranteed. If we take it's at most one. Yeah. So no, but what I want to say, there is a case when we see that there are the subclass has at least two functions. We choose this prediction, and then the prediction becomes correct, and then we don't know anything, but still we make no error, so we are in the same situation and no problems at all.
Yeah, but
no.
How wait, what? No problem. So if you don't make mistakes, you can kind of forget and start again.
And we forget and start again and just ignore the previous value of x.
Yeah. We can always do like that.
But why we are sure that the second class has at least two functions?
Because we are now in the case when h has at least three functions.
Okay.
So one of the classes has to have at least two functions.
Okay.
Mm-hmm. But then the other one has to have at most one function.
Mm-hmm.
And then the important point, how we can find which of the restrictions has at least two functions computably.
By waiting.
We just compute all the functions, no arguments in dovetailed fashion, right?
Yeah, okay. Yeah, so we just can enumerate functions from H. And start enumerating until we find that there are two functions.
Mm-hmm.
Okay. So
then you have to somehow to assume that the set of you have just one index, only an index for every function.
I assume that the programs don't repeat?
No. I think we just when we say
you can wait until you see another.
Yeah.
We have other values. We count the not the values.
I agree.
But okay, I don't know if it's clear, but okay, at least in case of dimension 1, we can always make at most one mistake. But in case of dimension 2, we cannot always make it.
Can you say again, what do we do when we have only two functions?
We just, I don't know, we predict according to the first one, and then when we are wrong, predict according to the second one. They are both programs, so we can do that.
Mhm.
Computable.
Mhm. Okay.
So somehow we can start proving
Okay.
dimension 2, maybe general case, I don't know.
Yeah, well, I guess we can try to go to the general case already. So what we will be doing is
So we are now proving the theorem in general case.
yes.
But for some
So-
reason, maybe you keep the statement of the theorem if it's possible to erase only part of the board. I don't know how it works.
mm,
No, if not, okay.
yeah,
Don't
no, I
worry.
guess we can. If Sasha doesn't mind, I can.
No, we can,
Move
yeah, we
that.
can erase this. If I can, but I don't.
Very strange happen. Things, they draw some random parts without any clear order. Okay.
Okay, so
So we have
So-
finite dimension and we need a computable strategy.
yeah, so what will happen is that we will we'll make some predictions, and we will ask at some rounds we will ask our enumeration to provide us with a new program, which will be somehow in our enumeration we will at certain point make, if we have some program F1 and we see that we make some prediction according to F1 and the adversary
So you explain the
tells us,
strategy or what you are explaining
yeah,
now.
I'm starting to explaining the strategy.
So the strategy deals with some x. So we are given some x and need to
yeah.
do
So
something.
I mean,
So what do
we'll
we
be
do?
playing the game. We'll be given some x, and we'll be enumerating programs to obtain some functions. This is some kind of our auxiliary variables of the strategy. We'll be getting some functions f from this enumeration of h. And
So we just enumerate the functions. Some of them go through at x, some go through 0, some go through 1. And we somehow, to decide what to predict, we need to decide what is more where do we have more variety, so to diversity, so we can choose this thing to exclude this.
yeah. So, but let's have a general picture when we can first. Let's try to understand when we can ask our enumeration of h to give us another function, and be sure that this function is there and we won't get into the loop. Because, for instance, if there are only two functions and we ask for a third function, then we might go into a loop and then our strategy won't be computable. So if we have some functions f1, f2 already to fn, and we see that what the adversary is giving us is disagree with every of this function, then we are safe. We can try to enumerate the...
No, the adversaries gives, we explain, the first step we are given just some x. Adversary doesn't give anything else.
No, but imagine that we are already playing for several rounds. There are some
Okay.
There are some functions that we already obtained from our enumeration, and we want to know whether in which situation we are safe to ask the enumeration to give us another function. So this will be happening only if we see that the points and the labels that the adversary gave us so far disagree with all the functions that we have obtained from the enumeration in the previous rounds. So this is the only moment when we would be asking our enumeration to give us a new function. Well, and what we will be maintaining in what our algorithm maintains is some collection of functions f1 to fk. And what our algorithm tries to do is to predict in such a way that we can guarantee that if we make some C to D mistakes, that will mean that the dimension of these functions that we have obtained must be at least D. And of course, this cannot happen too many times because we have the assumption that this f1, fk come from H, which has a bounded dimension.
Okay.
So
let me say again. So we enumerate our L, and the more we do it, the more function we know. So we
yes.
get an increasing list. On the other hand, we also because we already make some predictions and already they are true or false, each false prediction just decreases the list of functions because of I assume that prediction was made according to one of the functions, so it decreases the list of functions, and so it's kind of
Actually, it's not already true that it will be given with respect to one of the functions.
Yeah.
I mean, in some sense, so what Tomasz is saying is that, so, I mean, you can imagine that there is enumeration happening, but what we will do is that sometimes we will ask, so we have some, some x's and some values revealed already, right?
yeah.
Sometimes what we will do is just to ask for some function from the class that witnesses is that there exists a function that with that values that we have seen in the game at some moment, and this will be this f1, f2, fk that we will obtain from the enumeration of H.
Yeah. So of course, if we already have learned some values, then we can assume that we know we just wait until we get this function which goes through this value.
Very important that we will we will use old functions even if they are already inconsistent.
Yeah.
So you cannot just say that we will forget them.
Yeah, so for some reason we also use the function from the class which are inconsistent with known values.
Well, somehow, yes, but the point is that we want to argue that
so what we are trying to show that is that if we are able to obtain too many inconsistent functions, that means that H must have dimension bigger than D.
Yeah. So another point. So once again, we also ask for a new fi only when we make mistakes. It means that the number of fi's is at least, I mean that the number of mistakes is equal to the number of fi's.
So while we did not make a mistake, we just don't care whether a new function appear.
Yeah.
Okay.
We assume that we make a mistake every time in that sense. So when we make a mistake, we might put some function.
And if we don't make mistake, we just ignore this step, yeah?
Exactly.
Yeah. When we make a mistake, we put some function fi to the list. And so the number of functions will be the number of mistakes. Well, our goal is to show that we will make
But if we predict not according to our functions, and we just predict a value which doesn't exist with the function, then we don't get a new function. We just existing functions have different value. Why? I don't
No,
understand.
I mean, what
Why we are sure that there is
uh,
a new function?
well, because we assume that in the game there is some function from the class H. So we always can find, you know,
But
a
so
function
we
that is
always
consistent
predict
with what
according to some
adversary.
But say it again. We always predict according to some function from the class, from known function from the class, or
No,
not.
no.
But
We
if we
will predict
predict,
according to some majority votes over them. Not. I mean, it's complicated. So,
no,
but
but just a formal question: is it true that we always predict at least one of the functions is compatible with the new predicted values?
No.
at least one of the function is compatible with a new predicted value. Yes, but I mean, it's always true. It's like always 0 or 1.
No, maybe all functions go through 0, and then we never predict 1.
If all functions that we have on this X that we are obtained for prediction all have 0, then I guess we predict 0, right? Right, Tomasz?
I mean, all the functions that we have so far enumerated. I mean,
Yeah, in this F1, Fk, if they all are equal to 0, then we predict 0.
well, yes, okay.
But for example, you can, Sasha, you can ask a strategy. For example, the strategy is to always use the function which is consistent. I mean, the last function. Like, we make a mistake, we take a function which is consistent with what we've seen, and then we predict according to this function. Yeah?
Yeah. We take any function consistent with the last value.
Yeah, but this is bad. So it makes infinitely many mistakes on the class. For example, so imagine you have a class where you have all 0 function
Yeah.
and all functions that have 1, 1.
Yeah.
Then imagine, I don't know, you first get a function that is, well, I mean, like, then you enumerate, for example, you have enumerated a function which is equal to 1 on the first number. You predict 1, then it says it's 0. Then you can enumerate it and obtain a function that is 1 on the next number and 0 everywhere else. You start predicting 1, you again wrong, you know that there are 2 zeros. And now you obtain the function which is 1 on the third one, and so on. So from somehow the idea is that in that case, well, you've seen already 3 functions. You see that, well, these 2 that has been already wrong, they both predict 0 on the third number. And it's better to predict 0. Means that we will use functions that we know that are already wrong. Because the idea is that to argue that somehow about the global structure, the global property of the class, that we cannot have functions that can shatter a big tree.
Yeah.
Means that the old functions are also useful because. Okay, so with this idea, I guess
maybe one more specific question, and if it doesn't have a good answer, let's forget about this. But the question is, so it maybe we need some kind of non-constructive but finite advice to construct the strategy. If yes, what is this advice?
no, we don't need that advice.
Okay.
The strategy will be explicit.
Okay.
So we can start trying to
Yeah.
explain it.
Okay, so we want to do this inductively. So I would like to have some procedure. Let's say create dimension of k, and this procedure will, what it would do is it would call create k minus 1 some number of times, and I want to somehow argue that if I call this procedure with parameter k, then and then always if I make some c to the k number of mistakes, I obtain functions of dimension k. So suppose
Is
that
it
I
clear,
have
Sasha? What,
No,
for example,
no, I
what
don't know.
create?
Is it anyone who understands what is happening? Kolya, do you get what is happening? I am lost completely, but maybe you understand.
The following is happening. So Tomasz tries to present his strategy,
Yeah.
but still he is at the mere start. He just said the strategy is like that. It has a parameter k, and the strategy consists of this is not the same strategy. You have create dim and also create.
no, create dim. Yeah, that's
create dim.
one
Okay.
strategy that I want to call
strategy,
But
recursively.
Kolya, it is a strategy for prediction or some auxiliary strategy?
no, it's not auxiliary strategy. It's the main strategy.
Yeah.
But
It's a strategy, but it was
strategy for
important thing.
prediction.
For prediction, right?
Okay, but what is the argument of the strategy then? We need to predict something when we are given x. Which argument we use it?
We first of all we invoke the strategy with parameter k minus 1 and assume that k is already 0 or whatever. Oh, sorry.
No, I don't understand. So if we start our game and want to predict some value, we do it for which k?
Depending on
So we will be we will be calling this strategy k will depend on d. I mean, we will be calling this create dim with parameter d, where d is the dimension of the class that we can assume to know. And we can think that this strategy does some operation, and each step of this operation corresponds to a round in the game. And only if we, so this operation in this create dim will obtain some x from the adversary. We'll give it to the procedure create dim, and this procedure will give us some prediction, and we will be predicting. And two things might happen. Either we make a mistake, in which case we go to another loop in this create dim procedure, or we just forget about this game and go to a next round in the prediction game. So we obtain another x, we make a prediction according to what create dim tells us, and check if we are right or not. So we want to have some strategy which tells us how to predict, and we want to prove this that the strategy will do what we want to do by recursion.
So Kolya, so this create dim is not a function which returns the next move. It's kind of a process which is just a parallel process which continues after some predictions, some answer, and so on.
Create dim, it's very important. It can be seen as why it's called create. It creates some set of functions f1, fk in a sense. So when it terminates, the idea is that it can only terminate and produces some set of functions with some property. Well, I mean, for example,
but while producing
last,
the set is also making some predictions or what?
Yeah,
Yes.
it makes some predictions on the way, and it should, well, for example, create should stop working after c to the k mistakes. So when already c to the k mistakes are made, or something like that, I mean, some finite number of mistakes are guaranteed for the create dim to terminate and produce a set of functions of large dimension. Meaning that if we run create dim on a class with low dimension, it can never stop, and so we can never make this number of mistakes.
So this create dim somehow it has two effects. First, it plays in a game, and this is just our game, so we don't make any test games. It's just our game. But then either this is continued forever, and the number of mistakes is bounded,
or something,
or it terminates and returns a set of functions with some property.
Yeah.
This is the post conditions for create dim.
Exactly.
Yes.
Okay, and so what is this, the requirement for this set of functions then?
So this requirement, so ideally we would like this requirement to this condition to be that the dimension of the functions is at least k.
At least k.
And then since we know that these functions are obtained by enumerating h, we have a bound on, so we know that create dim terminates only if c to the k mistakes were made, and it creates a set of functions which has dimension k.
No, so if it makes more than c to the either it continues indefinitely and makes at most c to the power of k mistakes, or it terminates, it creates a set of function of dimension k.
Yes. So we know
that's all what you want from this function.
Yes, and this will be enough to.
Yeah, of course, because if the total size is total dimension is finite, then it's enough to start this process with large k, and it will never be able to create a long list, a list of high dimension. So the only way to satisfy the post condition will be to work infinitely with at most c to the k errors. Yeah.
Yes.
Yeah. So
okay.
So now this picture gets a little bit more complicated because so ideally I would use the condition of dimension, but dimension is a little bit hard to work with. So I will need an additional notion.
So we modify this plan. This will not, the explained plan is not what we will do.
So actually I will have something
because the induction doesn't work with just the dimension. We need to strengthen the inductive statement. So the properties of this function
Okay,
set
so
of
we
functions
change the
created by
plan
creating.
and require a kind of stronger post condition. Okay.
Yeah, so because for an okay, yeah, so I will just take the definition. So this definition is take some positive, some gamma bigger than 1, and we say that h is gamma advanced if for every non-empty subset A of H, we have the following, that the dimension of A is bigger than gamma plus log with base 16. The 16 is some magical combinatorial constant that comes from that we can just assume that it is what it is.
No, okay, 16 is not, I mean, it's just a
Yeah,
number that optimizes the bound in the end. But
yeah,
I mean, it could be other
Okay, so
number with some bound.
yeah, so let's try to understand what's happening in this definition. So first, what we can see is
No,
that
first I see that it's vacuous, because if A consists of only one function, dimension cannot be high.
What? I don't understand.
So
Why it's what?
you say for every non-empty subset A. Of course,
Of
A
H.
consists of one function, and then its dimension is 1, or 0 actually. And so we cannot have this thing.
But no, we can, because you look at the term. It's gamma plus something negative.
Negative.
Yeah,
Yeah, because it's a log of the size. I mean, it's so this log is in general. I mean, it's 0 for when when A is equal to H. For other A, I mean, this is
it's
something that the larger A is, the larger is this thing, but it's negative. So if
So, but if H is infinite, then it's always true then, or what?
well, that's always true, but we will apply it for finite sets
yeah,
that
yeah,
will
yeah.
be produced for the in the strategy. So I mean, the idea of this definition is that we want the dimension of every subset is large, but I mean, depending somehow on the size of the subset, and the exact formula is like that.
So, so instead of requiring that the function, that the procedure returns a subset of large dimension, we want that it returns something stronger.
Yeah.
Yes.
What is the stronger condition?
The stronger the condition is the dimension of every subset is large, well, given by this formula. So it will be gamma at 1. So I mean, so I don't know, like there will be
I mean,
a procedure that will create a gamma advanced set for some gamma, and then we will use it for increased gamma. So one.
Wow.
So I mean, the idea, I think, that we can increase gamma by 1/2 using 16 times the procedure for gamma. And in the end, to make to make dimension D, so well, one thing, notice that the set is gamma at once, and then it implies that the dimension is at least gamma, because if you look at this formula, right, so this implies that dimension of H is at least gamma.
Yeah.
So the plan is to make a D at once set But
So we
what
need
will do-
a set of large dimension with additional property saying that significant parts of the set also kind of have a large dimension.
Yeah.
yes.
Yes, in some way that the dimension is somehow evenly spreaded. Because what we want to do is we want to use this strategy creates dim will be doing some majority vote. And we want to say that if the majority vote is wrong, that means that at least half of the functions that we already have put some label y on x, while all the functions that we will see in the future put the opposite of y. And then if we are able to construct a set of big dimension, if we start with a set of big dimension and do majority vote on that set, we obtain this point where at least half of them are wrong. And we can imagine that we try to construct a set of dimension d after that. And you would like to have an argument that says, okay, well, we have now a set of large dimension on one side and a set of large dimension on the other side. They differ on x. So we can interfere that together they form a set of dimension d plus 1. But what can happen is that the dimension in this first set was somehow concentrated not on these guys that were wrong in the majority vote, but on the other half. So this kind of reasoning won't work with just the dimension, and we need this notion of gamma advanced instead of Littlestone dimension to be able to somehow work with majority vote.
Okay, so Koila, do you understand something? Maybe you can explain it to me.
Not this time, sorry.
But just what is happening, or kind of.
No. Sasha, what's the plan? So the plan is that, I don't know. So for example, I want a procedure that creates gamma advanced set. And then I want to increase gamma. So what I will do, I will run okay, let's say I have a precision that creates after, well, if it terminates, if some finite number of mistakes is made, it creates a gamma advanced set. So let's run this procedure. If it doesn't terminate, that we have a finite number of mistakes, some depending on gamma.
Yeah.
Well, imagine that then it terminates. Then what we will do, we will start do majority vote over this set. Well,
so the procedure terminates, and now we get a new point when we need to make a prediction. Yeah.
Yeah, and we make a majority vote on this set.
So the procedure itself makes some prediction for some point, and it takes care out about this, and we don't.
Yeah.
And now it's ended. Yeah.
And now half of the, well, I mean, some functions say that the value is 1, some, and some say that the value is 0. We predict according to the majority. So when we are wrong, it means that we have some, well, it means that half of the functions were wrong and the real value is 0. And now all the functions that we will obtain after that, they will be equal to 0 on x. And these functions will be equal on 1 to 1 on x. Because when we run,
yeah, and I don't understand. So you get this, you get a set of functions, and then you get a new value predict a new value according to majority, and then you see the correct value, and then what you do, you forget about the function which have incorrect value or not.
No, I keep the functions that have incorrect value. I will use them because I want to show, okay, then I will run again my procedure. I will create another gamma advanced set, but now all these gamma advanced guys, all these functions here are equal to 0 on that x that created a mistake here. It means that in principle, I can use it to like shatter a tree. Well, when
No, I
x
don't
is
understand.
0, I can
So
pick function
if you
here.
have a new advanced set, why this advanced set will be only made of functions which are zeros at x?
Because
each time we
because-
get a new function, we ask for a function that is consistent with everything that we saw so far. So this
and in this moment we
everything
saw that x is 0.
that means that every new function that we will ask in the future must agree with this.
No, but then you use some then you use some statement about your procedure. So its procedure doesn't just return the subset of H, which is subset of our class, which is advanced. It returns something specific, more specific.
No, I mean,
Well,
it returns a subset of H, but that's what I was trying to explain earlier.
No, you
are
have
able to get
H for two things. You have H for gamma advanced, which is and it is and also you have the entire class, I guess. Also, it was H. So it's now not clear which H you use, but
yeah. I mean, so the functions that we are obtaining by our procedure are elements of the class H, the big H.
okay.
So we will obtain some class T, some T,
but
which
this
is
new but there are functions in our big H which have value 1 at x also. Can they appear in the new set?
No.
Why? Who
Because,
guarantees this?
It is guaranteed by the way how we obtain these functions. Because we
so
only
you need
obtain
some property of the procedure, but which you prove by induction.
So it's very simple how we obtain. We only obtain a new function by doing this procedure: enumerate the sets of programs until you see a function H which is consistent with everything that we saw so far.
No. If you want, you prove your properties of your procedure by induction, or you use something else about the structure of.
We'll use the induction, but we have to say that's right, that the function produced by the procedure are obtained should be consistent with everything, with all the values revealed before the start of the procedure. So we must take functions that agree with everything. And well, the way you will always obtain a new function, you will make a mistake and you will enumerate your class until you see a function that agrees with everything and with this mistake, and put it in the list.
Okay, so I somehow lost. So maybe you can. No, maybe you can just somehow finish the argument, or at least the scheme of the argument, because of course we are already out of time. But and then we can think about, because it's interesting result, and it's very ingenious combinatorial argument. It's interesting to understand it. But maybe you can explain some kind of scheme now. And I won't interfere until you.
We have to somehow define exactly what this procedure does. So we'll have this create adv, which will be for parameter k. We'll call this create add k minus 1, and after that somehow obtain 8 to k new functions and do majority vote of them. Then throw away all the functions that were right and keep only those that were wrong. Well, and the proof, well, has of course 2 steps. So first step is that we have to obtain that, we have to notice that we can do that, this great add for dimension 1. So what this procedure does is just it obtains 60 functions and then do a majority vote of them. So what we can observe is that to obtain 60 different functions is enough to guarantee that if you have 60 different functions, then the set of 60 functions is 1/2 plus 1 advanced.
Yeah. So So what's happening is that let's try to explain a procedure that will create a 1 advanced set.
Yeah.
Of size 16, actually.
Of size 16.
So the procedure is just.
We are trying to generate 60 functions. And how do we do? So how can we generate a function? We enumerate first a function, and we try to predict according to this function. If we are wrong, that means that in the class there is at least 2 functions. So we can enumerate the function, the set of functions, until we see another function. And now we want to obtain a third function. We predict according to the second function. If we are wrong, we know that there must be a third function. And we can repeat that 16 times until we obtain 16 different functions. And then what we can have is some argument that if the sets, if you have 16 different functions, that it's enough to, it's immediately to see that 16 functions are 1 advanced.
So every set of 16 functions is 1 advanced. We can make a exercise. Why is that? Sasha, do you see why?
No. I want to see. I promise not to interfere, but so I don't interfere. But just I want to see the general scheme, what kind types of arguments appear and so on. So.
Okay, so this is one homework, I guess, to see that any set of 16 functions is 1 advanced. And now what we want to argue is that, okay, suppose that the procedure for some k, the procedure create advanced k creates if it stops, it obtains 1, 2 plus k advanced set. And we will use this assumption to argue that the create advanced k plus 1 obtains 1, 2 k plus 1 gamma advanced set if it stops. And well, I guess somehow it's the idea that Sasha was trying to explain here on this with these two sets, but now we don't have only 2 sets, but we repeat this procedure 16 times. So we will have 16 different sets, and we have to somehow argue that if every of these sets is gamma advanced for parameter k, then together all of them will be k plus 1. And now I guess to see what's really happening, you will have to slowly go through the details.
Okay, so
Well, I mean, let me try to say the idea very quickly. So again, so we create a gamma advanced set. Then we make a majority vote on some x, 1, I don't know.
yeah,
Then the half are wrong, for example. We leave this half. Then we create a new, on x1, we create a new gamma advanced set. We make a majority vote on some x2. If we are wrong, then we keep the wrong half. And so on. Some reason we do this, I mean, we do this some finite number of times, like 16.
yeah.
So when we have these halves, and we argue that now these halves form a gamma advanced set for some larger value of gamma, like gamma plus 1/2, that the gamma increases. And there are,
So
I mean,
we just take the union of all rejected sets.
Yeah. So you see these sets that I marked here.
Yeah.
So we have to argue that every subset has a large with little stone dimension, and there are 2 cases. Well, I mean, the point is that whenever you take a large, I mean, you have like these 16 pills, 16 parts. You can either take a lot. If you take sufficiently many in 2 different parts, then you can use this fact that, for example, if I take here and here, these guys are equal on one thing on x2, and these guys are equal to the other things on x2. So I use inductive hypothesis that both these parts of this have large little stone dimension, and then I can increase it by one. I can add 1 to this little stone dimension when I take the union. And the other story is when the other case is when I have, if I take a lot in one of the parts, but this a lot just the small fraction in this union of 16 stuff. So this here still the parameter gamma works for this subset.
Yeah. Okay. So, but what I think now we have some kind of a theorem. At least we understand the statement, and Kolya and me agree that it's a strange theorem and interesting theorem because initial guess was different. So something interesting happens here, and then there is some idea how this happens, but this I don't understand at all. So my suggestion is that Thomas can try to find someone who understands the proof by taking some participants and trying to explain the proof, and then this participant can repeat this proof in a cleaned form at some other future meeting. So maybe Sasha, do you understand the proof now?
Who? Me?
Yeah.
But I mean, it's our joint result. I don't know. Yes,
No. Okay, no. Just say yes. No, you didn't say whose result it is, so I just do. Yeah.
Well, okay.
Yeah.
No,
Okay,
I mean, it's our joint result.
Okay.
So for example, if you can volunteer to listening, then
yeah, and for example, Valentina, do you understand the proof?
More or less. I don't know.
More or less. And Kolya, I just want to check whether I am the only idiot who doesn't understand anything, or maybe there are some others.
I'm also an idiot in this set.
Yeah. Okay, so maybe then you can choose some candidates and prepare them for the explanation in a clean form. But it's interesting, some kind of combinatorial, very delicate combinatorial argument for a statement which is has kind of clear. And did anyone?
No, the idea is that we have to clearly understand this thing that happens with creating these functions, because then it's kind of not very hard combinatorics. But you
And just about the general position of this, did someone before you consider this kind of dimensions and strategies and computable strategies? What was known before you?
Yeah.
So to say.
Before somebody asked this question actually.
But who was this then?
When David and Hasrati asked this question whether there is always a computable strategy. And some other paper gave an algorithm that shows that yes, but they didn't know. I mean, they gave a strategy for that. I mean, they gave an algorithm in this abstract online learning with consistency oracle that implies existence of a computable strategy.
No, so the existence of a computable strategy was known, but not the bound.
Yeah, I mean, the bound was known. I mean, there wasn't the computable strategy was known, but the
bound was much bigger.
It was C to the D, and when we tried to look, it was something. C was about E to the 200,000.
So there was a bound, but very large.
Yeah, and we had 256 to the D.
Yeah.
Okay, but the proof was easier, or you simplified the proof and improved the bound at the same time.
We simplified
the proof is impossible to understand there. I mean,
okay, but this is not the difference with your proof. So, but the bound is better.
The bound is better, and the proofs are simpler, and they don't rely, for example, on the previous results and so on, where there are also some constants and so on.
So what you did, you improved the result and proofs and claim to have a simplified proof with better bound for a question which someone posed and which is combinatorially interesting. If it, I should say it secretly, it has nothing to do with artificial intelligence or real learning or whatever, but it's interesting anyway.
Yeah, it doesn't have anything to do with artificial intelligence. It has to do with machine learning. Usually, that's what's called.
If you understand machine, if you understand machine in a sense that it exclude any real machines, then it has different definitions.
Yeah. Okay. Yeah. So that's.
Yeah. And why have you? Why do you present your result as existence of computable strategy? As I understood from this discussion, you can use also this consistent oracle model.
Well, I guess the idea was that it's better to understand what's happening then. I mean, if there's just a question of, because it's too abstract, I don't know.
Yeah, I mean, I guess there are two questions and two independent questions, because one thing is that if the class H is infinite, then this algorithm which compares the dimension might not be computable. So we would like to have some different algorithm that maybe is computable but makes more mistakes.
Okay, can again, in which model you think it's also can be proven?
In the model with consistency oracle, as they explained it before.
The consistency oracle is when you can ask, given what was seen so far, some function from the class that agrees with what. And that's what we are using here. I mean, just we are giving an algorithm that just uses this kind of queries to the class, and in case when the class is enumerable in that sense, this oracle is computable, and that's it. So there is some abstract algorithm, and in application to this setting, it gives a.
So you never use the possibility just to enumerate some function in the class, which is not really not something needed to provide a consistent example of previous things. Yeah. That's
Yeah,
what
we
Kolya
only run it,
says.
I mean, knowing for sure that there exists something for the class that is.
So you're just waiting for from function from the class which goes to given points.
Yeah.
Yeah.
Yeah. Okay. So no. So maybe indeed it's very interesting indeed. But maybe you should first explain to someone else, and then this someone will try to, because not now the obvious candidate is Valentino, since it's close to the place of research. But maybe other people can be also used for that. If you choose some victim, you can try to use this victim for that. Okay, and what we have next time?
Yeah, next time the idea was to have Ibrahim Mamilov, but he has, I don't know, he doesn't have a tablet, so I will.
But he's where?
He's in Moscow.
Okay, but it's if he, no,
The MHEC.
I think if he's in Moscow, he can then, I don't know, come to Vereshchagin's place and use his tablet. No, it's not a serious problem, I guess. Or he should definitely have some friends with tablets. I cannot believe that this is not possible. So I guess you should organize this somehow. And so we assume that we will have his talk next time.
Yeah, and the talk is about so the
Majority of K arguments represented as a combination of majorities of smaller number of arguments. Yeah.
yeah, generalizing this Valiant argument that you can do this when you have majority on 3 bits. You can construct a log depth tree that computes majority on n bits. Now the result is that when you have majority on k bits, you can construct a tree for majority on n bits of depth log n base k, which is, I mean,
And the proof is also probabilistic.
the proof is probabilistic, but I mean, it's the same idea. You have to show that the probability will be large,
but the bound
there is
becomes
no
less
prediction.
trivial.
Yeah,
That's the difference.
that's kind of probable. I mean, it's just it's a result where you show the bound somehow. It's like a probabilistic result, but you have to.
Yeah. Okay. So let's decide that it will be next time, and with tablets which will be somehow found in Moscow. Moscow is a big city. There is a lot of tablets there. I cannot believe that it's not, or
I
at
don't
least
know what's happening now with tablets, but
and you at least he can dictate everything to you, and you can write if there is no other options, or and the week after that we have Gleb Novikov, who will explain about his research in ETH.
yeah, and he also saved us. He went for us in India at some moment. And asked Tomasz and Valentina. So he's a good man.
Yeah. So you, yeah. Okay. And just send the paper to the list of seminar. Okay. If you have some text, send this text.
Yeah. So I mean, you mean that was
just what was today. Just I guess it's there is somewhere in archive or whatever. So you can send the link or the paper, whatever you want, to the list, seminar list. Okay, no, very
okay, then see you next week.
Yeah, very impressive. Even confusing, but very impressive.
Thanks.
Yeah, we made everything to.
Sorry?
Thanks.
Thanks.
Yeah, okay.